In this lab, we are going to study another simple mechanical system, which is a simple pendulum, and we will use it as a precision tool to measure the constant of gravity at the surface of the Earth, g, ideally better than 1%. The pendulum is composed of a mass m attached to a rigid support with a massless string of length L. You can get the equation for theta using the Euler-Lagrange equation, and the resulting equation of motion is. Unfortunately, this equation doesn't have a simple solution for theta of t, and often we need to make an additional approximation that angle theta is small enough so that we can approximate sine theta by theta. The resulting equation of motion is the equation of motion for a simple harmonic oscillator. And you can easily check that the solution of this equation can be written in the form. So in this case, the period is simply given by. So the resulting period doesn't depend on the mass of the pendulum. It doesn't depend either on the initial or the maximum angle theta 0, but that's only true when sine theta can be approximated by theta. In fact, that this period is only valid for theta 0 of the order of 10 degrees, for which we have a deviation with the exact solution from this equation, which will be of the order of 0.1%. For larger angles, the deviation increases very rapidly. In general, if we want to probe the oscillation of the pendulum for larger angle theta larger than 10 degrees, we need to include corrections in the expression for the period, which will account for theta 0 itself. And these corrections can be found from this equation and lead to a period which up to second order in theta 0 can be expressed as. This expression is exact because the period t has, in addition to the initial value of the period we got for small theta 0, it has a correction in theta 0 squared, and it has also higher order terms in theta 04, theta 06, etc. But these higher order corrections will only become significant for angles theta 0 greater than 40 degrees. So as long as we remain at theta 0 below 40 degrees, we can neglect these corrections. In fact, at theta 0 equal 40 degrees, we have an error on the period compared to the exact solution of 0.1%. So we see that by accounting for the theta naught squared terms, we are able to describe the period of the pendulum for significantly larger angles than what we had in the small amplitude approximation. So in this lab, you will first test the validity of this equation by measuring the period t of the pendulum for different values of the initial angle theta 0. And for each of these value of theta 0, you will be able then to extract a value for g by rearranging this equation. And if you are careful with your measurement and pay particular care into reducing the uncertainties as much as you can, you should be able to get an expression for g which matches the one accepted for Canberra by 1% or even better than that. So one way, for instance, to get better uncertainties is to not measure the period for just one oscillation, but actually for a series of oscillations and then take the average. Of course, you don't want to do that for too many oscillations either, because after some point, the friction of the air acting on the bob will slow it down, and then the value of theta 0 will change. Other possible sources of uncertainties come from the support, if it's not perfectly rigid and moves. So you want to make sure that this doesn't move. And you also want to make sure that the string is really of a fixed length L and doesn't have any elasticity. As usual, it's important to evaluate the uncertainties for each of your measurements. So in the pre-lab exercise, we ask you to evaluate the uncertainty on G if you know the uncertainty on L and the uncertainty on T from this equation. If you don't know how to do that, please have a look at the video in the lab section in Wattle on analytical propagation of uncertainties. And of course, you can do the same thing for this equation. Now you will have to take into account also the uncertainty on theta 0. Then when you want to compare your measurement with the known value of G in Canberra, you can do that using the 3 sigma criteria which we introduced last week. And in the second part of the lab, you will have to test the dependence of the period with the length L. So you can do this for small amplitude, and in that case, you can use this equation. And then by plotting a linearized version of your data, including error bars, you should be able to extract, again, the value of G to some good level of precision. This part is very similar to what you did in the first lab when you were studying the oscillation of the spring, and therefore you should have all the tools in order to do your linearization and to extract the slopes, as well as the uncertainties. And finally, like last week, we want you to pay attention on your logbook and to submit it by the end of your session if you can. And if you're not sure what to put into your logbook, you can watch again last week's video, or you can also look at the marking criteria for logbooks, or discuss with your demonstrator what is expected, and also get some feedback from last week's logbook.